Most RAG failures start before search. Compare recursive, semantic, and proposition chunking, so your retriever gets better evidence from the beginning. You'll learn how the pieces fit into a workflow that ranks chunking strategies and picks meaning-preserving context. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Chunking sounds small, but it controls what your retriever and generator actually see. If your document is split poorly, the vector store indexes noise, and the model hallucinates. Good chunking makes each retrieval hit compact and relevant, which speeds things up and improves output quality. In practice, this matters on anything from a single policy page to a collection of a few hundred documents. At the core, we compare three ideas. Recursive chunking packs as much as will fit into a size window. Semantic chunking cuts where meaning between adjacent sentences is weakest. Proposition chunking treats each sentence as an addressable claim and filters by relevance. Each has different costs for latency, precision, and context size, and we keep one small corpus so you can see differences easily. We will build a tiny pipeline that takes one short policy note, splits it into sentences, and then makes 3 sets of candidates to score against a test query. You will see how sentence boundaries, windowing logic, and simple overlap-based signals change the context sent to the generator. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we make sentence boundaries explicit, so every later strategy shares the same raw pieces. This snippet turns one tiny RAG note into visible sentence units with Python re.split. The practical result is a clear list of sentences named sense that every chunker will reuse. The doc string mixes 2 small themes, refund policy facts and retrieval facts, and re.split cuts on sentence ending periods plus following whitespace. Sense becomes the shared input for every later chunking strategy, and the printed output shows sentence count and corpus size, so you get a stable baseline before comparing chunk behavior. What worked? Sentences are visible. What's missing? Sentences are tiny and not yet grouped. So, next we try a predictable size-based grouping. This example builds recursive-style chunks by filling a window until the next sentence would exceed limit. The outcome is a set of size-based chunks created by carrying a buff, checking room for the next sentence, and starting a new chunk when adding it would cross that limit. Raising limit usually keeps more context together, but can pass unrelated text downstream. Lowering it reduces noise, but risks splitting connected facts. The output reports how many chunks were created and the longest chunk, which helps you pick limits that balance context with focus. The size baseline is clear but blunt. Next, we look for a meaning-aware split that tries not to sever ideas. This snippet finds the weakest adjacent meaning link and turns it into a chunk boundary. What you get is a semantic cut that avoids slicing through a coherent idea just because a size counter ran out. Here, words creates tiny token sets. The loop scores each neighboring sentence pair, and cut lands after the pair with the lowest overlap. That lexical overlap is a teaching simplification for an embedding-based similarity score. The output shows where the semantic boundary landed and how weak that link was, which makes the split explainable instead of only size-driven. You can tune the overlap threshold to prefer more or fewer semantic breaks. We still might be carrying unrelated claims inside a sentence group, so let's isolate claims and filter for the query. This code stores each sentence as an addressable proposition and filters only refund-related claims. The useful result is a list of props with small IDs beside each claim and hits that select claims whose words overlap query terms. Treating each sentence as a proposition is a compact teaching stand-in for a stronger proposition extraction step. The output shows total claim count and the matching refund claims, which points toward tighter context with less unrelated material. Handy when the retriever only needs 1 or 2 facts. Now we compare the 3 candidate sets against one query and pick the least useful context. This example compares recursive, semantic, and proposition chunks as tiny retrieval candidates for one query. The snippet scores the same need terms against every strategy, keeps the top matching text from each candidate set in best, and then sizes measures how many unique words that winning context would send to the generator. Winner picks the leanest top match. The overlap score here is intentionally small for the demo. In a deployed RAG system, you'd use embeddings, hybrid retrieval, or a re-ranker. The output shows which strategy returned the shortest useful context, linking chunk design directly to cleaner generation input. So you can choose by compact usefulness rather than intuition. Mapping this toy into a real project is simple. Swap the toy note for a set of support articles. Replace lexical overlap with embedding cosine similarity, and use a small vector index for candidate retrieval. The pipeline and decisions stay the same, but you get real-world recall and precision by using embeddings and a proper re-ranker. These are 3 practical ways to turn text into retrieval candidates. Use the size-first baseline when you need speed. Pick semantic splitting when keeping ideas intact matters. And choose proposition-level pieces when you want precise, addressable claims. One caveat: smaller chunks cut down noise, but can lose linked facts that require multiple sentences. For a concrete next step, swap the lexical overlap score for embedding cosine similarity, and measure how FAISS nprobe changes which strategy wins on your support dataset. Tune nprobe and the embedding model to see how semantic splitting moves from explainable heuristics to robust retrieval. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.